This lab is about the motion of a falling object, and the net forces acting on the system is non-zero. To do this experiment, I recorded a video, obtained data from observation, modeled my experiment, and compared the observed versus the predicted. The fundamental principle I used for this lab was Newton's second law, which once again states that the final velocity will equal the initial velocity plus the total net forces acting on the system over the mass of the object times the change in time. Once again, we can also use this equation to predict the motion of our falling object with a certain time delta t. In this experiment, the total net forces acting on the ball that affect its falling motion are 1. The force of gravity pulling it down, and the air resistance that pulls it up. The force of gravity is pulling the ball down at approximately 9.8 meters per second squared, and is much greater than the air resistance, which has little effect on the ball. Here is my tracker video.
This video shows the ball going down at a non-constant velocity, speeding up in the negative y direction, while the drag force is going in the positive y direction that causes the ball to slightly slow down. By looking at the graph over here, you can tell that the velocity is not constant because the graph is not in a straight line. By looking at the data, we can get some of our initial conditions. One is the time start at 0. Another is the initial x component. Finally, we have our last time at 0.667. The reason my y component is put in my x component is because my original video was flipped horizontally. So I had to flip it back and change the axis, and now my y would be in my x coordinate. When given the code, I had to put in some initial conditions. One of them was a tennis ball's mass, which I found to be 0.057 kilograms. Another was the ball's original position, which I explained before, started at negative 0.003. The ball started at 0 for velocity as it was starting from rest. Time started at 0 as I explained before. Our delta t had to be really small as our video was so short. We have our gravitational constant set at 9.8. Our j-hat vector, which shows the y-axis, has an up for a positive direction. To start off our model, we're not going to worry about b, as that has to do with drag, and I will model that later. Another initial condition we have to input is our time, which I had 0.7. That was when my experiment ended, when the ball hit the ground. This is the equation to set up the weight force of gravity acting on the ball. Here is where we inputted our fundamental principle of Newton's second law and our equation to find position. With all of our initial conditions good to go, we can run the program. Running it gives us this. Here is the graph with my predicted and my observed, orange being observed and blue being predicted. As you can see, my prediction goes way over what my observed was. This is because we did not take into account for the drag force. To fix our graph, we have to go back to our program and take into account for the drag force. Here is the equation for the drag force. So when we take our F net, we are adding the weight force plus the drag force. The weight force being the negative y direction and the drag force being in the positive y direction. We also had to find a b that suited my case. After trial and error, I found a b that to be 0.04, b being our proportionality constant for the drag force. Running it gives us this. After going back and replotting it, here is my final graph. As you can see, it's a lot closer than when I didn't account for drag force.
Terminal velocity is when the drag force is eventually equal to the force of gravity and would cause the object to fall at a constant velocity. In neither case is this true, as the line is never straight. You can tell it's always curved, showing that there's an increase in velocity. Had the ball been thrown down instead of being dropped, the terminal velocity will still probably never be reached, as it's such a short time. It might exceed how fast it was going before, but terminal velocity is when the weight force and the drag force are equal, and it'll travel at a constant velocity. In this case, that will never happen. It's not going at a constant velocity. Thank you for listening. My name is Seth, and have a nice day.